So as I said, next Tuesday is actually day 15, so your day 15 quiz questions will be due by Tuesday of next week. And we're just catching up a little bit and reviewing today. So the first topic that was asked about by someone in the class was on intermolecular forces. So how do you identify, if you're given a structure, what type of intermolecular forces the molecule would be capable of? And so I've got some structures here that we can use to discuss this question. Let's take a look at the first one here. So if you have a structure that's only carbon and hydrogen, so it's a hydrocarbon. If you have a pure sample, meaning all the molecules have the same structure, the only type of intermolecular forces that will be capable of is London forces. And that's because that molecule exists as a series of nuclei that are surrounded by electron clouds, so they're molecular orbitals that surround the nuclei. So there's multiple orbitals, but collectively all those orbitals add up together to create roughly one kind of cloud or multiple clouds of electrons, and each of those orbitals or clouds of negative charge can shift around, slosh around randomly to one side or the other, and so that can create temporary partial charges. And so normally when we think of a molecule, especially in Gen Chem when we're dealing with smaller molecules, normally we think of the molecule as having one dipole, one negative side and one positive side. But when you start to get into bigger structures with more atoms, and there are lots of different molecular orbitals involved, any one of the electron pairs in any of those molecular orbitals can shift one way or the other, so you get multiple individual clouds of electrons that can shift one side and create areas of small partial charges on the surface of that structure, maybe somewhere else on the structure. There's another shift of electrons, and I create a couple more partial charges. So that's why when it comes to London forces, the surface area is the biggest factor. The more surface area there is, the more instances around the surface there will be where small quantities of partial negative and positive form, and then those can line up next to identical molecules and attractions can form between them. If this molecule were in a mixture, so not all of the molecules were the same, it would depend on what it's mixed with. So obviously if I mix it with another hydrocarbon that's non-polar, because there's no electronegative elements to permanently pull electrons to one side or the other, and the only shifting is going to be random due to the electrons just kind of sloshing around randomly in their clouds, that's just still going to be London forces. But if I mix it with something that's polar, like this compound here, because the chlorine is more electronegative, significantly more electronegative than the carbon it's bonded to, it will permanently pull the electrons it's sharing, the molecular orbital that has electrons surrounding it. Those electrons will shift to one side and create permanent opposite charges on opposite ends. And that's known as a dipole. The word dipole refers to a single molecule having opposite charges on opposite ends of its structure. So if this molecule were to come in contact with the other molecule we were looking at, the nonpolar one that doesn't have any real electronegativity differences, the dipole of the one structure would induce a dipole upon the other, or the area of positive charge here that's permanently on these carbons due to the chlorine pulling electrons away from them is going to attract electrons from this cloud toward it, since opposite charges attract, and that will create an induced dipole. Which is also a type of London force. So if my molecule is nonpolar, it can really only form London forces. Either a dipole, induced dipole attraction like this one, or an instantaneous induced dipole. Both of those are types of London forces. So this one, instantaneous, just means randomly for an instant, not due to electronegativity differences, just due to random shifting of the electrons, the molecule creates partial charges. And then if another molecule comes nearby of the same type, or any two nonpolar molecules, if one of these for an instant does have an area of negative, that will induce the electron clouds in the neighboring molecule to shift accordingly to create the opposite charge there so that they can attract. So that's an instantaneous dipole where one molecule forms a random dipole for an instant, attracting to an induced dipole where the other molecule forms charges in response to the first molecule, so electrons can shift away and avoid repulsion, and that actually exposes some areas of opposite charge to attract. So that's a nice little summary of London forces for you. If I have, so I don't really leave enough space there. So let's talk about the structure a little bit. So in this molecule, because it has a dipole, if we had a pure sample of it, its types of attractions would be dipole, dipole. And that's because one molecule has oppositely charged ends due to the electronegativity difference, causing electrons to permanently shift to one side. Now it's still a cloud of electrons around there. So even if the molecule is capable of dipole-dipole, because it has a permanent dipole, and a neighboring molecule can come in and align its areas of positive and negative. If both molecules have permanent negative end and positive end, then they can line up really easily. They don't have to wait for electrons to shift around randomly because the electronegativity differences already caused them to shift. And so that attraction is where one molecule's dipole attracts another molecule's dipole. That's why we have the term dipole-dipole. The word is there twice because we have two molecules attracting. So anytime a molecule is polar, it's capable of dipole-dipole attractions in a pure sample with another identical molecule. It's capable of dipole-dipole attractions with other different molecules as long as they're also polar and they have permanent partial opposite charges on opposite ends. Are these molecules capable of London forces? Yeah, anything's capable of London forces. So the electronegativity difference here between the chlorine and the carbon predicts I'll have a negative end and a positive end. But the cloud that these shared electrons exist in, that molecular orbital, is still a cloud, it's still fluid, it can still shift around. So through random shifting, there will be moments where the electrons shift even more in one direction, creating an even larger quantity of partial negative and partial positive, so the attractions can be stronger at times. And that adds to the attraction between those structures and means that we would also have London forces in addition to the dipole-dipole there. Can this molecule engage in hydrogen bonding at all? So it definitely can't hydrogen bond with another molecule of the same type because all the hydrogens are bonded to carbon. Anytime hydrogen's bonded to carbon, the electronegativity difference is minimal. So carbon will usually be a little more electronegative. And so I might have some small charges there. But hydrogen bonding requires the hydrogen to carry a large partial charge so it can attract to some element with a large partial negative. If the quantity of partial charge is minimal, it's not meeting the threshold required to be labeled a hydrogen bond. So any molecule that has all of the hydrogens present bonded to carbon will never be able to hydrogen bond using those hydrogens. We could consider the possibility of this chlorine's partial negative forming a nice strong attraction with the hydrogen of, say, like a water molecule, because in a water molecule the hydrogen's bonded to an oxygen, which is one of the most electronegative atoms. Electrons shift dramatically and I get a very large partial positive on that hydrogen. So this hydrogen is set up to hydrogen bond. The problem is the chlorine isn't carrying enough of a partial negative. So that's why we say for a hydrogen bond to exist, we need a hydrogen sandwiched between two highly electronegative atoms. It needs to be covalently bonded to one, so the electrons will be pulled away to create a large partial positive there. And it needs to have another highly electronegative atom with a large partial negative to attract. So this is almost a hydrogen bond. The chlorine's not quite electronegative enough. And that's why we want to recognize that only nitrogen, oxygen, and fluorine are electronegative enough to typically carry enough of a partial negative to attract to a hydrogen, to form a hydrogen bond. Just got your message there, Zoe, so we can definitely address that after this. So if my molecule is polar, it's going to be capable of dipole, and London forces, and maybe hydrogen bonding, depending on whether it meets these requirements. What about the structure here? The structure here, what type of intermolecular forces will it be capable of? Well, due to it, yeah, go ahead. Say again?
London forces.
Good. There's always London forces. Will it have dipole-dipole?
I think yes.
So when you're looking for a dipole-dipole, you first want to make sure you can establish that the structure actually has opposite charges on opposite ends. So you want to look at the geometry of the molecule. In this trans version, these two carbons are sp2, which means they're flat, and the dihedral angle between these two chlorines is 180 degrees, so they are pointing in opposite directions, and that makes a big difference there. So because they're both attracting electrons and creating partial negatives and partial positives, to establish that there's a dipole, you'd want to look for opposite charges on opposite ends. Like this molecule here had a negative on one end and a positive on the other. So where is the negative? Well, it's on two different sites. So to deal with a situation like that, you want to look for where is the average position of the negative. And so if I have negative on this chlorine and negative on this chlorine, the average or central position to those negatives would be right in the middle. But that also happens to be the average or central position to the two positive sites, as well as, even if the hydrogens carry charge, it's also central to the positions of the hydrogens. So when a molecule has a certain degree of symmetry, like this structure, and you can show that the average position of positive and negative charges are all right in the center, it's not polar. It doesn't have a dipole. So even though it has individual sites of positive and negative that might line up and be able to form some attractions with other molecules, we don't consider it to have a dipole, so we wouldn't label it as being involved in dipole-dipole attraction.
So in order to be involved in dipole-dipole attractions, it has to have a permanent dipole, not just like a dipole moment?
Correct.
Okay.
Yep. So this structure is nonpolar. It really would only be capable of London forces with other molecules of the same type. What if we made these chlorines fluorines? Would that make a difference?
No.
Good. So it's still symmetrical. It still has opposite charges that average out to be centered in the same location. Is this structure capable of hydrogen bonding?
Yes. I
Good.
think so.
Yeah, so because it's a fluorine rather than a chlorine, wherever the fluorine is attracting electrons from the carbon, there's a big electronegativity difference there, so these quantities of partial negative are quite large. It's got the ability to attract to another molecule through a hydrogen bond. Can it attract to another molecule of the same type through a hydrogen bond like this? Is this a hydrogen bond attraction?
No.
Good. Yeah, this is not a hydrogen bond attraction because the hydrogen is bonded to carbon and the electronegativity difference there, as we said, is minimal. This is a small quantity of partial positive. The hydrogen has to be sandwiched between two highly electronegative atoms, not between one low electronegativity atom and one high electronegativity atom. So that particular structure, it's not going to let me erase that. That particular structure is not going to be able to hydrogen bond with this molecule. Will this structure here be able to hydrogen bond with this molecule?
Yes.
Good. Right, so here, because the hydrogen is sharing electrons with an oxygen, the electronegativity difference there is going to create quite large partial positives and negatives there. So that fluorine can attract nicely to the proton of that structure. So the big electronegativity difference here creates a large partial positive, partial negative, and then the large partial positive and negative between this hydrogen and the fluorine can attract. That's the hydrogen bond. I just want to re-emphasize that. Students often make the mistake. The hydrogen bond is not the covalent bond. It's the intermolecular attraction between two opposite partial charges on different molecules. Can this structure here hydrogen bond?
Yes.
Sure, it sure can. It's just like the other one, the OH. Anytime there's an OH bond or an NH bond, you've got a big electronegativity difference that creates the large partial charges necessary to form those attractions. So is it correct then to say that this structure in a pure sample where all the units look like this is capable of London forces, dipole-dipole, and hydrogen bonding?
It wouldn't be dipole-dipole, would it?
Yeah, so it would really depend on the rotation of the bonds. So the way I've drawn it prompted you to say that, and it's what you've said is correct from that perspective because, as we said before, if all of the partial positives, all on average, are centrally located in the center due to the symmetry of the structure, and all the partial negatives are also on average centralized in the center, it shouldn't have a dipole. So we would say, well, it's not capable of dipole-dipole. Well, now that we've talked more about bond rotation, we know single bonds can rotate. We want to keep in mind the possibility of these carbon-oxygen bonds rotating. So if I rotate not the double bond, so I'm not talking about putting the two OHs on the same side, because that would require the pi bond to rotate, and that can't happen unless I increase the temperature a lot, because I have to break the pi bond and then reform it after the rotation. Just talking about rotating the single bonds, I could rotate one of those and the structure could look like this. So now I've got large partial positives on these hydrogens, some pretty large partial positives on the carbons because the oxygen's pulling electrons away from them, and my large partial negatives are on the oxygens. So on average, I've got multiple areas that are carrying some positive. The average amount of positive is going to be somewhere in between those areas, maybe centered right around here roughly. The average position of negative will be centered between the oxygens, which will still be kind of really close to the center, right between those two oxygen atoms. So if the positive and negative are not in the exact same location, that will create a bit of a dipole, and that does then set the structure up to dipole-dipole with other structures. Any questions about any of that? All right, let me look at Zoe's question. That was 4.55a. So that's probably at the end of chapter 4. Too far. There it is. Yeah, this is a great question. Let's take a look at this one. Alright, so in this question here, we're trying to judge which of these is more stable. And their hint, you may find it helpful, is a bit of an understatement. You definitely need to draw the chair conformations here unless you can imagine them in your mind, which is very difficult, to determine which of these is more stable. First of all, what's the relationship between these two structures? Are they identical? Are they stereoisomers, constitutional isomers, no relationship, enantiomers, diastereomers? Well, they're definitely not constitutional isomers because they both have the same cyclohexane parent chain, and they both have 3 methyl groups on carbons 1, 3, and 5. So they'd both be 1,3,5 trimethyl cyclohexane. The only difference between them would possibly be the RRS configuration. So then I would want to look at, are they mirror images? So they're not constitutional isomers. That means they're either identical or they're mirror images that are non-identical, which would make them enantiomers, or they're diastereomers, which is the last option as once you eliminate all the other options. So they're definitely not identical here. If this first structure were drawn like this, then they would be identical. Because this structure with the 3 methyl groups sticking out at you could be flipped over like a pancake. If I just flip it over like a pancake, it'll look exactly like this structure, and all 3 methyl groups would be pointing away. So these two are identical. They're the same, which means they would have equal stability, and if I drew the chair of one and flipped it over, it would look like the chair of the other. Right, so that's obviously not what the question is asking. I just wanted to point that out. So because this structure does not have the 3 methyl groups all pointing out at me or all pointing away from me, it's different from the original one. And they're not mirror images. If I drew a mirror here and tried to draw the mirror image of this one, what would it look like? Well, this dashed wedge would be reflecting a dashed wedge there. This one would be reflecting a dashed wedge here. This one would be reflecting a dashed wedge here. So the mirror image of the structure is the same structure. if I draw the mirror image of a molecule and it's the same as the original molecule, then I know these two are identical. And when mirror images are identical, they're not enantiomers. Enantiomers are only non-identical mirror images. And so if a molecule is identical to its mirror image, it's a chiral. So that also is a relevant analysis. So since these two structures are only different in the spatial positioning of the groups, dash wedge or solid wedge, but they're not identical and they're not mirror images, that means their relationship is that they are diastereomers. And another way to help you recognize diastereomers is when you have diastereomers, each chiral center, some of the chiral centers have the opposite configuration between the two structures, and some of the chiral centers have the same configuration at the between the two structures. All right, but we want to actually answer this question. So we'll call this structure number 1 and this structure number 2. So let's draw the chair for structure number 1. So some of you may like to draw a chair like this, where you start with the feet first and then draw the head. Some of you might like to start with the head and then draw the feet on the right hand side. Either is reasonable. The important thing here though is to recognize that a solid wedge is pointing up from the ring and a dashed wedge is pointing down. Right? So there's no rule that says a solid wedge is axial or equatorial necessarily, but a solid wedge is going to be up. So if I want, I can look at this as being carbon 1. My solid wedge would be coming up. So at this carbon, the up position happens to be equatorial. It alternates around the ring. On the first carbon, up is equatorial. On the next one, up is axial. On the next one, up is equatorial. On the next one, up is axial, and so on. So I want to try to draw the most stable one so I can do a comparison, right, between these two. So if carbon 1 is up, and I go around the ring to carbon 3, that being up, those are both equatorial. And then I go around the ring, 1, 2, and the next one is down. That one's axial. If I were to flip the ring, this is not flipping it like a pancake. This is doing the ring flip where I take the feet and push them up and take the head and push that down. That would give me this structure, where now I've got 2 axial groups and 1 equatorial. So if I were comparing the energy of these two flipped versions of the same structure, structure number 1, this one would be more stable and this one would be less stable. Especially when the large axial groups are on the same side of the ring, they're going to be really crowding one another out. And if you make a model, you'll see they're much closer than they look like in this drawing. And that'll cause steric repulsion between those electron clouds and make that one unstable. So this will be an equilibrium that will greatly favor the more stable flipped version. And so that's the one we want to compare to the other structure if we want to see which one's more stable overall. So now let's look at structure 2 and draw the 2 chairs for that. There's one. Do the flipped version. Here all my methyl groups have dashed wedges. So there I would want to start carbon 1 with my methyl group down. All the dashed wedges means down. So 1 is down, 3 is down, and that one's behind, right? So this is in front of that, which is why I cut that line to indicate that it's behind that other line there from the chair. This is 1, 2, 3, 4, 5. And the methyl group on 5 is down. So this is really unstable. To put all 3 large groups in axial positions on the same side of the ring, they're really going to crowd one another out. And so that would very quickly flip to the other chair version, and it would almost never have the energy to flip back. And when it does flip, these are still in down positions, but here the down positions are equatorial positions. So this one is way more stable of these two, and it's also more stable than the most stable version of the other one. So if I can get all my groups into equatorial positions, nearly every single molecule exists in that form at any given moment in time, and those are overall more stable than a structure that puts one of those groups into an axial position, again, because it will crowd out through 1,3 diaxial strain the other axial groups. Even if they're hydrogens, they still get their electron clouds close enough to repel a little bit, and so that makes that less stable. So this would be the more stable molecule. So having all three of my methyl groups on the same side of the ring makes them more stable, because when they're positioned 1, 3, and 5, it gives them all the opportunities to be in equatorial positions. Any questions about that? All right, other questions that y'all have? You're welcome, Zoe. Any other specific questions or bullet points from the study guide anyone would like to discuss, or the remaining exams for those of you who have not taken exam 6, or we could get into exam 7 material, which is going to be on Tuesday and Wednesday of next week, and obviously Thursday of next week as well.
I have a question regarding the exam for this week and one of the bullet points.
Sure.
It's the first one for day 11, skill review. It's explaining the difference between positive and negative, and not specifically the R and S configuration for plane polarized light.
Right. All right, so this is not easy to draw, but so that bullet point is about, mainly it's about making sure you understand that a given enantiomer will rotate plane polarized light either in a positive or negative direction, and that is not necessarily correlated with its R or S configuration. So let me try to give you an example to illustrate that. So let's say I've got this here molecule right here, and maybe I've got a chlorine here versus the enantiomer of that. So there's a couple different ways I could draw the enantiomer. One would be to, if I want to draw an enantiomer of a structure, draw the structure exactly the same in every way except any solid wedge in the structure. Let's go back. I don't like that line, it's too messy. Let's try this again. Any solid wedge in the structure would be made into a dashed wedge. If there's an odd number of chiral centers, this will always make an enantiomer. Alternatively, I could have imagined a mirror plane there and drawn the reflection in the mirror of what that would have looked like. Usually we draw the mirror to the right of the structure, but you can draw a mirror anywhere. If you have the mirror image of the structure, that means these two are identical, and they are, because if I flip this one over, it looks exactly like that one. So either one of these is the enantiomer of the original structure. So maybe we want to quickly determine for each of these whether their chiral center is R or S. So this one here, got my chiral center. I got to prioritize the groups attached based on their atomic numbers. So what's attached initially? There's a hydrogen that isn't shown here. There's a carbon here. There's a carbon here. So the chlorine has a higher atomic number than carbon and hydrogen. That's priority 1. These two carbons have the same atomic number, but this one's bonded to hydrogens, which have a lower atomic number than the carbons that this one's bonded to. So this would be priority 2. This one would be 3. And when the fourth priority group is pointing behind, if I go clockwise, that determines that that configuration is an R. if I have the mirror image and I do the same analysis, it's not, the priorities of the groups are not going to change. This one ends up being counterclockwise, so that one is an S. If I were to look at this structure here, same analysis. In this case, though, the fourth priority group is pointing out at me. So when I have a clockwise rotation, if the fourth priority group is pointing out at me, that one is S. So as we said correctly, this structure and this structure are identical. They're both the S enantiomer. So if I have a pair of enantiomers, I know that if I made a mixture of them and it was a 50-50 mixture where half the mixture was R and the other half was S, I would see 0 optical rotation. However, if I take a pure sample of R, it will rotate the plane polarized light. It will rotate the plane that that light is traveling on to some degree. Can I say whether the R will rotate it clockwise or counterclockwise or positive or negative? No. Not without doing an experiment. So if there's ever a situation where you need to know which direction the plane of that light will rotate as it's passing through the sample, if I don't give you any information other than the fact that it's an R or S configuration, there's no way for you to answer that. If I told you that the S version at some temperature rotates the light in the negative direction, then I know the R would rotate it back in the positive direction. Right? So a pair of enantiomers will always rotate at the same temperature. They'll always rotate the light in opposite directions to the same degree. But if I just have one of those, that bullet point is about recognizing that we can't really tell whether it's going to be R or whether it's going to be S. Hopefully that answers your question. Any other questions about anything?
Can we do an example problem from the book?
Sure, which one?
3.51. I was looking at maybe either doing E or G.
All right. Let's take a look. All right. E or G. Yeah, well, we can talk about both of these. It won't take very long. All right, so here we're trying to identify the most acidic proton in each structure. Typically, the most acidic proton is not going to be one bonded to a carbon. Right? So these protons that aren't shown are usually overlooked by students, but in this case it's not that big of a deal usually to do that, because if a proton on a carbon were removed and the electrons stay behind as a lone pair, it would create a negative charge, and that would be an especially unstable negative charge to exist on a carbon. So usually we're looking at heteroatoms like nitrogen or oxygen or some other element like sulfur or something. They're much more stable with the negative charge, and as we said, if we're judging neutral structures and their ability to act as an acid, what we want to do is to draw the conjugate base and see which is most stable. Which will stabilize the negative charge on the conjugate base most effectively. Because if the negative that's left behind after the proton leaves is stable, through either solvation, having a low quantity of charge. The atom holding it is either large or electronegative. There's resonance to stabilize it. There's induction to stabilize it. Or it's positioned in a compact orbital close to the nucleus. Some combination of those factors will help us to differentiate. The more stable the charge is, the more likely the proton's going to be picked off and leave behind a negative. So if I were to pick off this proton here, I would have this structure with a negative on this oxygen. How would that be? Is there anything to stabilize it? Well, oxygen's, as an atom, pretty good at stabilizing a negative because it doesn't have a lot of shielding and it can pull the electrons close to the nucleus. But on the other hand, since it's so small, having an extra negative means that the charge ratio of negative to positive isn't very close to 1. And so that makes it a little bit unstable. In this case, is there any resonance or anything to stabilize it? Unfortunately, no, because there's also a proton here. This carbon is sp3 hybridized, and so there's no way to shift those electrons around. There's no highly electronegative atoms to pull the electrons away through induction. So this doesn't look that great. It doesn't look terrible because the atom stabilizing the negative is relatively good at stabilizing it, but it's not great. So what about picking a proton off of this nitrogen? Well, that would give you this structure here. If I pick a proton off of that nitrogen, it already had one lone pair, now it'll have two, and it'll make a negative there. How's that compared to this structure? Well, a negative on a nitrogen is not as good as a negative on an oxygen for a couple reasons. One, because nitrogen has fewer protons, so putting an extra electron on it is going to make the ratio a little bit more deviating from a 1-to-1 ratio, and so that makes it a little unstable. And also, because it has fewer protons than the oxygen, it's just not able to pull the electrons, and its second energy level is close and form as nice of attractions there. So that's definitely not a better option than our first option. But this one here is going to make this one is going to be the answer, because once I pick that proton off and imagine what the structure looks like, I see a couple things. What's happening here? Well, I've got a negative on an oxygen, so that's very similar to the first situation, but there's resonance. This oxygen can shift electrons in here and move them over here. And so since there would be multiple resonance contributors, 2 resonance contributors, in reality, the true structure would have only half a negative on each oxygen, so that would be much more stable than putting a full negative on an oxygen here. There's also something here that isn't really captured in this acronym. Does anyone see it? It's an intramolecular hydrogen bond. Not intermolecular, intra, so within the molecule. So not only is this negative here stabilized through resonance, so only half a negative on each oxygen, it's also stabilized by an attraction because of the electronegativity difference here, creating a large partial positive on this hydrogen. There's an attraction. These two elements are pretty close together. 5 and 6 membered rings don't create much angle strain, so these elements are kind of like pointing at one another, and the negative positive attraction between them will also help to stabilize it. So that means this proton is even more acidic than it would normally be, just being stabilized through the resonance. There's an extra hydrogen bonding attraction there. It's kind of similar to solvation, but it's not the solvent coming in and forming a hydrogen bond or attraction. It's another functional group on the same molecule making an attraction there. So real quick for G, what we see here, we've got 3 protons that are similar to this one, where if they were lost, the negative charge would be stabilized by resonance in each one of these cases. So what's the difference? Well, one difference is we've got a couple chlorines over here. So what impact do they have? Well, the chlorines are there because they can create induction. As they're relatively electronegative, 2 of them, especially pulling a pairs of electrons away from this carbon, is going to create some positive there. And that carbon is going to attract electrons from this carbon and increase the amount of positive here. And so if the proton leaves and I get a negative, that extra attraction will help to pull some electrons away from that negative. So any electronegative atom will, through the bonds attracting in that direction, create waves of partial positive coming out from there that can stabilize through attractions, or you can think of that as pulling sigma bonds away from that oxygen so there's not quite as much negative around it. That helps to stabilize it as well. So in this case, this proton right here is the most acidic. What about the other 2? What if we had to rank them? So this would be the most acidic. Which would be the second most acidic? Well, these 2 are very similar, not going to be a big difference. Neither one has anything beyond the resonance that we talked about here to stabilize the negative charge after the proton leaves. The only real difference is over here there are 2 hydrogens, and over here there are 2 methyl groups. So what impact will those methyl groups have on the ability of this negative charge to be effectively stabilized? That has to do with sterics. Right, so we talked about solvation. If there's a lot of sterics around a charge, it makes it harder for the charge to be stabilized through solvation. Right, so normally if I have this COOH and the proton's lost and I have a negative charge spread out through resonance, so really I have like half a negative on each. Maybe there's this big structure here. If the rest of the structure is a big bulky structure, it makes it harder for the solvent molecules, whatever they are, if they have some permanent dipole or maybe even only a temporary dipole, they're going to have some ability to form opposite charges. And so the solvent will stabilize a charge by bringing in partial charge of the opposite type to form an attraction. So if there's a lot of sterics in the structure and it's got this big bulky group like these big methyl groups and they're kind of blocking out a fair amount of that, it makes it hard for the solvent molecules to bring lots of partial positives in to form attractions with the area of negative and stabilize the negative. So this negative here that would result on this oxygen after this proton is removed would be a little bit more stable than the negative that would result on this oxygen due to the fact that the hydrogens are not very sterically hindering and they don't block the solvent from coming in and forming decent attractions there, whereas these methyl groups are a little bigger. They probably block the solvent from coming in a little bit. Especially if you made a model, you'd be able to see that happening a little bit more. So this one would be second most acidic and this one would be third most acidic. So that'll be a legitimate question that you might have to answer at some point, like on the final exam. Questions about that? Other questions?
Could we go over a couple more bullet points from day 11?
Yeah, let me bring up the bullet points so that you don't have to read them off word for word. Alright, so this would be study guide for exams 4 through 6. So we're looking at day 11 here. Which one are you thinking about there, Ethan?
Can we just start with the second one?
Sure. If I have percentages of R and S, I want to be able to determine enantiomeric excess. So let's look at that. Alright, so I'll just make one up. Let's say I have a mixture of two enantiomers. Let's say, let's keep it simple at first, let's say it's 50% R and 50% S. What is the enantiomeric excess?
Would it just be one?
So if the enantiomeric excess were 1, that would mean that 1% of that mixture has either excess S or excess R. If they're both in exactly equal amounts, there is no excess. I've got equal amounts of both of them, so the entire mixture is a 50-50 mixture. So the excess is the amount of R or S beyond what's beyond what is a 50-50 mixture. So if the whole thing is exactly 50-50, it's not 0%, it's not 1% excess, it's 0% excess. I don't have any excess if everything is exactly 50-50. So what would it take to get a 1% excess? Well, 1% excess would mean that 99% of it is a mixture. That would mean I've got 49.5% R and 50.5% S. So it's almost exactly 50-50. For every 49.5 molecules of R there are 49.5 molecules of S plus one more. So there's an excess of 1 out of every 100 molecules is S, and the other 99 out of 100 are a 50-50 mixture of the two. So the excess is the amount beyond the 50-50 mixture. So what if I had 40% R and 60% S? What would the enantiomeric excess be there?
20%.
Good. So the way to think about that is if 40% of it is R, I want to figure out how much out of that total 100% is a 50-50 mixture. Is anything beyond that is going to be the excess. So if I have 100 molecules, out of 100 molecules, 40 of them are R, 40 of them are S, and then there's another 20 that are S, right? If there's 60 S out of every 100 and 40 R out of every 100, I can think of this breaking down in this way. So really I've got 80% of the mixture is a 50-50 mixture, and the other 20% is the excess S. So the percent EE would be 20% S. And the rest, the remaining 80%, is a racemic, which means it's a 50-50 mixture of the two. It doesn't have to work like this with nice round numbers either. We could look at a situation where, you know, I could just make up some more numbers. So let's say I had 73% R and 27% S. What would the excess be in that case? Well, what I can do is I can subtract these two numbers, right? Because if I know that some of it's going to be a 50-50 mixture, I can take the smaller amount and subtract it from the larger amount. And whatever I end up with that I have left here, that should be excess. Because for every 27 S's, I want to subtract 27 R's, because the 27 R's and 27 S's make up the 50-50 part. And by subtracting the amount of R that matches with the S to make the 50-50 part, the remaining amount after I subtract is going to be the amount in excess. So that would be 46% excess, and then 54% racemic. Any questions about that one? Other questions? You want to look at some more of these bullet points?
Yeah, I would like to look at a couple more.
Which ones?
Can we just go down the list?
Sure. Alright, so here we're given an excess and an optical rotation for a pure enantiomer. We want to be able to determine the amount that's R and the amount that's S. So, get rid of some of this stuff here. I wrote this question before, anticipating we might want to look at an example like this. So here I've got a rotation of plane polarized light is measured to be negative 15 degrees for pure R. I want to determine what's the percent EE and the ratio of R and S, which is what that bullet point's asking about, if I have a sample with a measured rotation of 3 degrees. So what this question is saying is, if I had a sample that didn't have any S present at all, it only had the R enantiomer, that would cause a rotation of negative 15 degrees. So the first thing I notice here is, if the pure R is known to rotate the light in a negative direction, but then I put my sample in and I see some degree of rotation in the positive direction, what does that tell me about the sample?
S would be strongly positive.
Good. It tells me that I have excess of S. Because any part of the sample that's a 50-50 mixture is going to cancel out and give zero rotation. If I see a rotation in a positive direction, it must be due to an excess of the opposite of an enantiomer that caused the rotation in the negative direction, which is known to be the R. Good. So what do I do here? So what I want to do is to use that formula where I'm looking at the observed rotation for the sample, and I divide that by the rotation for the pure sample, and multiply by 100. That gives me the percent enantiomeric excess. So that'd be the first part of the question here. I want to do that first. Before I can get the R to S ratio, I got to get the percent EE. So the observed rotation would be 3 degrees. The pure rotation for the S would be what? If I know I have excess S because it's rotating in the opposite direction from what the excess R rotated, I want to compare the observed S to the pure S. And so if the pure R rotates in a negative 15 degrees, the pure S would rotate in a positive 15 degrees. So if I put that in my calculator, I believe I get 20%. Let me just double check that here. 3 divided by 15 is 20%. So that's 20% excess S. If I had a 50-50 mixture, the rotation would be 0. I see a slight rotation in the positive direction because I have slightly more S. That's not being canceled out by the presence of R. So if 20% of the mixture is excess S, what's the deal with the other 80%? Is it R?
It would be a 50-50 mixture.
Right. So I'm only seeing rotation. I'm only seeing rotation from the excess S. The rest is not causing rotation. That's why I only see a little bit of rotation. The rest is canceling out, and that means the rest must be racemic, or a 50-50 mixture of R and S. So if I break this down into a 50-50 mixture, that's 40R and 40S. And so what that gives me then is a total of 20S here that caused the rotation, plus the 40S here that was being canceled out by the R. That gives me a total of 60S for every 40R. Or 60% S, 40% R is the same as 20% excess S. Questions about that? Alright, so that was this bullet point here. Be able to determine if a molecule with chiral centers is chiral overall and whether it is achiral in a meso compound. This bullet point here. I think I wrote something down related to that. Here we go. Got some structures here to look at. So how do I determine if a structure is chiral or achiral? There's a few different ways to do that, but there's only one that doesn't have any exceptions. If I want to show that a molecule is chiral, there's one method that has no exceptions, and as long as I do the method correctly, it will always work. And that is draw or create with a model the mirror image and see if the structures are superimposable. If two mirror images are superimposable, then neither is chiral. The structures are achiral. If the structure is not superimposable on its mirror image, it's a chiral structure. So what does superimposable mean? It means by rotating the molecule in space, flipping it over, rotating on its side, or rotating any of the single bonds, it can be made to look exactly like the other structure. So two structures are superimposable if they're identical through any rotation that doesn't require bonds to break or form. There's a shortcut you can take if you think the molecule might be achiral. If you can find a mirror plane that splits the molecule, meaning one half of the structure is a mirror image of the other half of the structure, that is a good analysis to do, because if you find a mirror plane that causes one half of the molecule to be a mirror image of the other half, that means that it's a meso compound. Meso compounds are always achiral. They're not superimposable on their mirror image. They are superimposable on their mirror images because they're identical to their mirror images, and they also have a mirror plane that splits the molecule in half. So it's kind of a two-layered test you can do there to confirm a meso compound and to confirm that it's achiral by showing it is identical to its mirror image. So this first structure here, just a quick example, I can quickly see this is a meso compound. I recognize that there's a mirror plane right here. Even this methyl group, a mirror splits the methyl group, where one hydrogen is a reflection of the other. This group here is a reflection of this group. So if I have a mirror plane where one half the molecule is a mirror image of the other, that's a meso compound. It's achiral. Maybe I want to confirm that with the other test. That way I can be even more confident in my answer. So if I have the structure, I draw its mirror image. The mirror image should be superimposable upon the original structure if it's achiral. And that's where you can make a mistake, because if you're doing it in your mind and you're not seeing how they're identical, you can make the wrong conclusion. These two structures are identical. I have to take this one, or the other one, and rotate it in space 180 degrees. So if I take this carbon and rotate it over here, I'm not picking it up off the plane of the paper or flipping it over. I don't have to do that in this case. I'm going to take this carbon and rotate it over here. The molecule will just look exactly like this. So that confirms that the structure is achiral, and also that the mirror plane here confirms that it's a meso compound. If I look at this structure here, I don't really see that. I don't have the mirror plane. If I imagine a mirror plane here, this methyl group doesn't reflect onto this one. Because this one's coming out of the plane, it's reflecting onto the hydrogen that's here. And since a hydrogen and a methyl are not identical, they're not mirror images of one another. And likewise, this methyl group would be reflecting onto the hydrogen that would be here. And they're not identical. So only if the groups reflecting in space are identical groups will there be a mirror image or a mirror plane that splits the molecule in half. So this is not a meso compound. If it's not a meso compound, that doesn't necessarily mean that it's chiral. So I would still want to draw the structure and then draw its mirror image and see if the two are superimposable. And this is much easier to do with a model. So no matter how I rotate this one in space, I could try to flip it over, I could try to rotate it around, I could even try to rotate the carbon-carbon bonds, although that wouldn't be helpful in this case since the parent chains are both zigzagged and spread out. To line up the parent chains, I could flip the molecule over, or I could rotate in space. No matter how I do that, one of the groups on this molecule is not going to line up perfectly with the group on the other molecule. So these two are not identical. They're not superimposable. And if you don't believe me, I encourage you to make a model. And if you do that and still don't believe me, I encourage you to bring your models to lab so I can help point that out to you. So if it's not superimposable on its mirror image, this is a chiral molecule, and its mirror image is it's enantiomer. These two are enantiomers of one another. If you're given a structure where the chain is kind of bent here instead of zigzagged all the way out, you probably want to definitely make the model of that. I just drew this here to point that out. You could imagine if you want to get this zigzag all spread out, I've got 1, 2, 3, 4, 5, 6, 7 carbons there. So if I did spread the zigzag out, it would look like this. In order to do that, I'd have to rotate around this carbon-carbon bond, and when I do, it would create this structure. So if you're not seeing in your mind how this dashed wedge would rotate up above the plane and be pointing out at you as a solid wedge once this carbon-carbon bond rotates to put the zigzag all in one plane, that's definitely where you should be making a model. To demonstrate that to yourself with a model is much easier to see with a model. And you'll be able to use your model kits on the exams now throughout the rest of the semester. So what about this compound? Well, this compound is also achiral, and it's also a meso compound. If we made its mirror image, it would lie directly on top of it. And there's a mirror plane where one half of the molecule is the exact reflection of the other half, which makes it a meso compound. Any questions about that one?
So for that last one, all you did was rotate the bond.
Yeah, for this structure, to make it go from here to here, I just rotated this carbon-carbon bond. So if you have your model kit and you want to try to put it together real quick to see that now, you're welcome to.
Okay. I'll probably do it after all this.
Yeah, that's fine. It's just I only had to rotate one bond. So you want to look at examples where you have to rotate bonds to make sure you can do that with your models and get try to look for structures that look identical or what their relationships are by rotating.
Okay. Yeah, I think I see it.
Did anyone else have a question? Alright. If anyone does that, I'm going to keep going through these bullet points unless anyone has any other specific questions they would like to ask. Please interject. I don't want to monopolize the whole discussion with just some of these bullet points. Okay, so this bullet point here we've kind of talked about already. How do I know if a molecule is chiral or achiral? Looking at the chiral centers is one way to do that. If the molecule has an even number of chiral centers, I need more analysis. If it has an odd number of chiral centers, it will be a chiral molecule. Looking for a plane of symmetry. We just talked about that. The plane of symmetry we're talking about here is the mirror plane. If there's a mirror plane of symmetry where one half is a reflection of the other, it's definitely achiral and it's definitely a meso compound. If I can't find a mirror plane, that's a bit tricky, right? Because in the original structure here, there's nowhere where I can draw a mirror plane. I could try to draw a plane here. This half is not a reflection of that half at the moment. It requires that bond to rotate for them to find a mirror plane. So it's not just a mirror plane at all. If there's any rotation of the single bonds or of the molecule that I can make, where in any one rotational form, half the molecule is a mirror image of the other half, then it's a meso compound and it's achiral. So if I find that there is a mirror plane, I know it's achiral. If I can't find a mirror plane, I can't necessarily say for sure that it is chiral. If I have the ability to run tests on it in the lab and I have a polarimeter on hand and I can test its optical rotation, that's a good way to see if it's chiral. If it doesn't show any optical rotation, it's either achiral or its enantiomer is present with it in a 50-50 mixture. But if it's chiral and it's pure, it should give an optical rotation that's measurable. But this last one here is the ultimate test. If I can draw or make a model of the molecule's mirror image and I find that it is not superimposable on its mirror image, then I know that it's chiral. There are no exceptions to that one. So there are multiple tests you can do, but you should definitely combine any test you plan on doing with looking at whether the molecule is superimposable upon its mirror image, because if it is, it's achiral, and if it's not superimposable upon its mirror image, it's chiral. I'm going to skip over this next bullet point. I don't even think there's a question on the final exam that relates to this, and that's how much of a distaste I have for Fisher projections. And the next bullet point as well. This bullet point here relates to rotational conformations of a molecule. And that, it kind of relates again to what we just talked about here. So, what's the difference between this structure here and this structure here? They're rotational conformers. Or one is just a different rotational conformation of the other. By rotating one of the carbon-carbon bonds, I can get this one to look exactly like the other one, so they're not unique. They're the same structure, just rotated differently. So that bullet point is to point out to you that if you see a structure in one rotation and it looks chiral, it doesn't mean that it's chiral. You've got to look for any rotation. If you can find any rotation where half the molecule is a reflection of the other half, then you know it's achiral. But ultimately, any rotation of the structure, if you draw its mirror image, you may have to rotate some of the bonds or flip the structure over to see if the mirror image is superimposable upon it. So that test should still work in the same way. Any structure I give you in any rotation, if you make the mirror image of its current rotation, and then see if those molecules can flip on top of one another, or if rotation is somehow needed, if through any type of rotation, without breaking or forming any bonds, you can show that the structures are superimposable or identical, then you know that molecule originally was achiral. The next bullet point, please jump in if you have other questions, is about, not seeing any other questions on the chat. The next question is about chiral resolving agents or affinity columns. So those are two methods that are used to separate the pairs of enantiomers. So when we're talking about this example up here, we said if I have like a 50-50 mixture of the R molecule, and mixed in there is the S molecule, and I have both of them present, and if I look at their structures, what's the difference? Well, the only difference is the spatial positioning of the chlorine and the hydrogen at this chiral center. So these two structures have the same polarity, they have the same solubility in different solvents, they have the same boiling point, same melting point. I can't use any of the techniques we've talked about this semester to separate them from one another. I can't use recrystallization or distillation or chromatography, standard chromatography at least, to separate these, because they're going to have the same affinity to silica gel, they're going to have the same affinity to an ion exchange column, same boiling points, same solubility in any solvent. I'm not going to be able to take advantage of any of their different physical properties to separate them when they have the same physical properties. So a resolving agent wouldn't work well with these structures. There are limitations to resolving agents. But the idea of a resolving agent is to add a second chiral center. So let me just redraw these structures since there's so much clutter over here. So let's say I did this again. So here was the one enantiomer, and here's the other. Oops, those are the same. So to use a chiral resolving agent, what I would need to do would be to add another chiral center. So if there was some reaction, I've got these two mixed together. I want to separate them physically from one another in the lab. So I've got this mixture, and I would need to do some kind of reversible chemical reaction first. That'd be step one. If I could convert, let's say we just have another carbon here to make things a little easier. If I could convert this carbon into a chiral center on both structures, I could convert this pair of enantiomers that don't have physical properties into a pair of diastereomers that do have physical properties. So maybe I do a chemical reaction where I'm able to convert this carbon center here into a chiral center. Maybe here I'm able to add another chlorine. So we'll ignore for the fact how difficult that would be synthetically. But let's just say we did that in here and here. So I have to add the other chlorine in order to, in the same configuration on both structures. Now these two are no longer enantiomers. They're diastereomers. Why is that? Well, they have the same configuration at one center, but then they have different configurations at the other center. It's got to be a reversible reaction, though. So there's a lot of limitations here that means this is not going to be practical for many situations. So I'd have to do this reaction, get the two chlorines installed with the same configuration so that I create a pair of diastereomers. Now they have different solubilities, slightly different polarities, and so they might run through silica gel at different rates, and I could separate them that way, or they might have different boiling points or solubilities, so I could look at doing a distillation to separate them, or possibly a recrystallization if they were solids. So then I could separate them. Since they're now diastereomers, I can separate them from one another, and then that would give me these structures. Separated from one another. Once they're separated, I would still have to reverse the reaction. So somehow I'd have to be able to remove that chlorine again and get back the original structure. And at that point, since they were already separated, I will have effectively removed the one enantiomer from the other. That's a long, difficult process, so it's not necessarily the preferred method. It requires two reactions because I have to install this group and then remove it. And that takes a lot of time and energy and money. So it's not something you'd want to have to do, but sometimes if you've got a pair of enantiomers and those two structures have different medicinal properties, you have to separate them. You can't give someone a drug if this is a medicinal molecule that has another molecule that creates side effects. You have to remove it, and so you need a technique to separate those. So the other technique in that bullet point is about chiral chromatography. Chiral chromatography is like silica gel chromatography, except instead of using silica gel, you're using little pieces of plastic or tiny little ground up polymer that has groups positioned in a specific arrangement to form attraction. So I might use, if I want this to be the molecule that I am isolating, it has my medicinal properties, I might use it as a template and mold a polymer around it. And the details of that we don't have to get into, but if this thing has a specific three-dimensional shape and the chlorine's pointing in a certain direction in space, and I can mold around this a structure that has a cavity here for this molecule to fit into, and then I can take these structures and pack them into a column. Very crude drawing, obviously. I'll pack this into a column. Then I could take my mixture and pour my mixture into the column, and as the S enantiomer and R enantiomer pass through there, since the S enantiomer would be able to fit into this cavity. There might be something in here with a partial positive that the partial negative of the chlorine could attract to, positioned in just the right way in space, so only this chlorine would attract to it, and if the chlorine's pointing in a different direction in space, it wouldn't form the same attraction. So this S enantiomer would travel through slowly, and the R enantiomer wouldn't be able to form the same type of attractions due to its spatial difference, and so it would travel through more quickly. So I would collect in test tubes the R coming out first in some test tubes, and then I would bring in another test tube later to collect the S when the S comes out. So that's the gist of how chiral chromatography works. Questions about that? Should I keep going? Does anyone have any other questions?
I have a question.
Yes.
We can also keep going over day 11, but regarding day 12, could we do a similar example to the quiz question regarding entropy? And then could we also do an example of drawing a reaction coordinate diagram for a given reaction?
Yeah. Entropy. Which quiz question? Was that the one where you had a reaction given with reactants and products?
Yeah, we were given, I think it was a ring structure, and then we had to assess the entropy.
Okay, yeah, let's talk about determining the signs for delta S. Alright, so if you're given a reaction, let's say we've got this reaction here. And I want to convert that into actually, yeah, let's do this. I want to convert that into this structure here using water. So how do I judge the entropy change? So there are a lot of subtle details related to entropy, like the state of matter and the temperature and things like that. But what usually takes priority over all of that is looking at the number of moles of reactants versus products. So any reaction where I'm combining reactants to make a fewer number of moles of products should usually have a delta S that's negative, because even if one of my products has a lot, or even if one of my reactants has a limited rotation or limited vibration and the variety of the molecules individually isn't that great, if I have multiple molecules, the ability for them to move around independently creates a lot of variety or entropy. And if I bond them together into one structure, even though there's more ways that the bonds can rotate and vibrate in this structure than there are in any one of these individual structures, if they remain independent, they can move separately in different directions, and there are more total particles to bounce around and create a lot more variety and disorder. If I combine them together, there's almost always less. So the best shorthand way of judging the sign for delta S is to look at the moles on either side. It's very unlikely that I would give you a reaction where there are maybe equal moles on both sides and ask you to judge entropy. There'd have to be some information about the state of matter in that case. So, for example, if I did this reaction where water as a liquid reacts with this structure here, maybe it's also a liquid, and maybe a different reaction occurs where the water breaks the structure down into this here, just make up something. And so maybe these two combine to make a solid. So if I have 2 moles of reactants and 2 moles of products, then I can't use this to determine which side has more entropy. But if I'm converting liquids into solids, then I know, again, the entropy would have to go down, because the particles aren't moving around much. They're just lined up next to one another. There's lots of vibrational freedom and variety, but I don't have the translational motion that creates the translational variety when the independent molecules can move around and slide past one another in a liquid or a gas. So the state of matter can make a difference, but mainly it's about the number of moles of particles. So if we're looking at this reaction, and I know delta S is negative for the system, because I have more entropy to begin with when the particles are greater in number and have more variety and freedom and they can move independently than when they're stuck together. How do I determine delta S for the surroundings?
Is that looking at delta H?
Right. So I can't judge delta S for the surroundings unless I know delta H for the system. The surroundings are not going to involve any bonds breaking or any change in the structures. So I'm not going to change the state of matter or the number of moles in the surroundings. The only thing that can change in the surroundings really is the temperature. And the temperature change in the surroundings depends on whether the reaction is releasing heat or absorbing heat. So if I don't tell you any information about delta H, you'd have to try to judge it. And the best way to do that is to look at, from what we've talked about so far, maybe if there's a charge on one side or the other. If the charge is more stable on one side, then it's probably got a lower potential energy than the other side. Or we can look at the pi versus sigma bonds, which would be the case here, because I've got this pi bond breaking. I've got to break a sigma bond in the water, but then I form a new sigma bond here. And also a new sigma bond here, because there's no OH bond there. So this oxygen would pick up a hydrogen and form a sigma bond. The OH would come in here and form a sigma bond. So breaking a sigma and a pi to form 2 sigmas is the key that allows me to determine the sign for delta H. So I have to remember that when bonds break, energy must be absorbed. I have to put energy in. But if the bond isn't that stable because it's a pi bond, it doesn't absorb that much energy. So that would be a situation where if I'm looking at the potential energy, I don't have to put much energy in to break the pi bond, but then when the new, more stable, lower in potential energy bonds form, it's going to go down in energy. And so that would be a situation where on net, it's exothermic. So it's releasing heat into the surroundings. The temperature of the surroundings goes up. So the particles in the surroundings have more entropy. There's more variety in the way the particles will vibrate, rotate, and translate if they're at a higher temperature. There's a broader distribution of motion, more variety of motion. And so I can say that the change in entropy for the surroundings would be positive in that case. That's why exothermic processes are generally favored, because they produce more entropy for the surroundings, and ultimately whatever produces more entropy for the universe, combined system and surroundings, is going to be a favored or likely process to occur. So hopefully that answers your question about entropy. You're interested in reaction coordinate diagram. So here is a question about that. So I might ask you to draw a reaction coordinate diagram and give you some information to guide you. Any reaction coordinate diagram that I ask you to draw is probably going to ask you to plot the free energy. So you can write free energy here, or G, which stands for Gibbs free energy, same thing, versus the reaction progress. I might tell you how many steps the reaction is. Each step in the reaction requires an activation energy. So wherever the reactants are, for a 3-step process, there's going to have to be 3 different transition states, 3 different times that bonds have to break and then reform before it can produce the products. So we got to refine this using more information given. So I know there's 3 steps, and then it says where step 1 is the slow step. The slow step, what does that mean? That refers to the bottleneck of the process, or which step is really slowing the whole thing down. The slow step, it's like an assembly line, right? I can't do the second step until the first step happens. So if the first step is a slow step, it means it doesn't happen very often. Once it does, as soon as an intermediate forms, since one will only form once in a while, there will be a higher chance that that undergoes the next step before another intermediate forms from the first step. So whatever step is the slowest actually needs to have a higher transition state peak than any of the subsequent steps. So I would adjust that and make sure that it's clear that whichever step is the slow step has a higher total energy it has to get to compared to the other steps. It also tells me here that the reaction is exergonic. What does that mean? It means it releases free energy. So it's like exothermic, but it's not just looking at the potential energy of the heat. We're also looking at the free energy. So if I'm plotting free energy, exergonic is the same for a free energy plot as exothermic is for an enthalpy plot. But if it's exergonic, that means the final energy has to be lower than the initial energy. So I would make sure that my reaction coordinate diagram clearly shows that the products are at a lower free energy than the reactants. If it then asks me to label delta G, I can say delta G is the quantity of energy comparing the starting with the final energy. Delta G has nothing to do with what's happening in between. It's just the initial versus the final. The change in free energy, in this case, would be negative due to the decrease in free energy as the reaction progresses. Activation energy, there may be multiple activation energies. Activation energy is the energy I have to put in to get from the reactants to the transition state. So that would be activation energy 1. Once I reach an intermediate, depending on how high in energy that is, it might not take much energy to get to the next transition state. It might take more. If the second step were the slow step, this peak would have to go up higher than the first one. But that quantity of energy difference between the transition state and the most recent intermediate, that's the activation energy for the second step, and then I'd have some activation energy for the third step. The intermediates, call those A and B. The intermediates are the local minima, where when this first reaction occurs, it produces something. That something can continue to react forward or it could react back, but it's relatively stable compared to the transition states on either side of it. So some quantity of that will probably accumulate. It might be very small if the next step happens more often than the first step. So I'll get very little of that to exist in solution, but there will be some quantity of it because it has to form and wait for another collision to occur before the next step can occur. The transition states occur at the top of the peaks. So there will be a transition state, for each step in a reaction. The transition state does not accumulate in solution. The transition state is a local maximum. So as soon as these bonds break enough to get to this really high energy point where the electrons are no longer in the correct orbital shared nicely between the nuclei, or even in a lone pair, they're not really in a proper orbital, those electrons are really unstable. So when that happens, it will immediately react back or immediately react forward. Really, one molecule at a time will probably form this. but as soon as it forms, it's so fleeting, it reacts so quickly, it never accumulates in solution, and there's no way to even really measure its existence. None of the instruments we have are fast enough on the time scale to get any spectral data for it or structural data for it, because it reacts as soon as it forms. It's like trying to take a snapshot of a tennis ball at the peak of its height when you throw it in the air. As soon as it gets there, it starts falling right away. It's too fast to really measure. So then, which points on the diagram affect kinetics? Kinetics is all about activation energies, especially the activation energy for the slow step. Right? If it's a slow step, as soon as it happens, the rest of the process is pretty quick. So the overall rate of product production from reactants really is only limited by how often that first step happens. If the first step happens 50 times a minute, well, then the whole process will happen about 50 times a minute, because as soon as the first intermediate forms, it's going to react quickly before the next one occurs. So this first step is really slowing the whole thing down. It's the transition state energy or the activation energy for the slow step that affects how often the product is produced, which is what kinetics is measuring. Thermodynamics is about equilibrium. It's about measuring when a process reaches equilibrium, not how fast does it happen or how often is product formed, but when it reaches equilibrium, am I going to have more product or reactant? And that is only really impacted by delta G, or the difference in free energy between the reactants and products. The bigger the difference here, the more the equilibrium will favor the side with a lower free energy. Questions about that? All right, well, we're out of time, but I'm just going to keep going if anyone has more questions. So feel free to fire away if anyone has more. Otherwise, I'll just kind of go back and probably look at some more of those bullet points. Anyone? Alright, so now we are getting into chapter 6 here. Why does potential energy change when bonds break? How does that affect the temperature of the surrounding? Anytime bonds break, it's always an increase in potential energy, right? You got to think about potential energy as the potential for change in position for the particles. Right? So if the particles are already bonded, whatever type of bond it is, if two atoms are already bonded, well, then their electrons already are in a molecular orbital surrounding both the nuclei, attracting to them. What potential for change is there? Well, there may be some potential for change, because if another reactant comes along, maybe look at chlorine. If another reactant comes along and a collision occurs, it's possible that different orbitals, different molecular orbitals between the hydrogen and the chlorine, which has 17 protons, maybe different molecular orbitals would stabilize those electrons better because they can get closer to protons and form more attractions. So if the initial electron arrangement isn't as stable as it could possibly be, there's some potential for rearrangement. That's what potential energy is. But if all I'm doing is breaking a bond and going from the molecular orbital to individual atomic orbitals that no longer overlap, and I don't have the construct of interference, well, now it's never going to be as stable. Now there's the potential for it to go back. It's a higher potential energy because with the atoms farther apart, there's the potential for them to get closer, reform the molecular orbital that stabilizes the electrons in a position where they can attract to both nuclei. So breaking a bond always goes up in potential energy, and forming a bond always goes down in potential energy. That's why when we see a reaction and we're plotting potential energy, we always see wherever the reactants are, we always have to go up in energy first to break the bonds, and then depending on if the new bonds are less stable than the original ones, maybe it stays kind of high in energy. Maybe the new bonds can't stabilize the electrons as well. And so there's potential for it to go back. Or maybe if the new bonds are more stable, the potential energy goes down, because if it's more stable and the electrons form stronger attractions, there's not much potential for it to go back. And so you can think about potential energy as the potential for particles to rearrange their positions in space due to attractions, or also potentially to avoid repulsion. So that covers these two bullet points. Oh, what about the temperature of the surroundings? Well, we know that if the potential energy on net goes up, energy can't be created out of nothing. It has to come from the surroundings. So that would be a temperature decrease for the surrounding. The kinetic energy of the surroundings has to be converted into potential energy for the potential energy to go up. If the potential energy on net goes down from the initial point to the final point, that energy can't just be destroyed, it's got to be released into the surroundings. So that would cause a temperature increase. The surroundings would increase their kinetic energy because they're absorbing the energy that the system releases or emits. And what if bonds break and produce other bonds? We actually just did talk about that. If it's exothermic, that means from the system's point of view, it's releasing energy in the surroundings so the temperature goes up. If it's endothermic, from the system's point of view, it's absorbing energy from the surroundings so the temperature in the surroundings goes down. Temperature is always going to be for the surroundings, because that's the solvent or the container or whatever, and that's where you're going to be measuring the temperature. Any questions on any of the bullet points or concepts from day 11? Before we move on to something else. Did anyone else have any other questions? Or Ethan or anyone, did you want to talk about any of the bullet points in day 12?
Yeah, if we have time, can we also go on to day 12?
There's a lot of them.
Yeah, just any of them, I guess, would help.
Well, let's go over some of the questions I prepared. That should help with some of those bullet points, and then we can fill in the gaps with anything that we don't get a chance to talk about here. So let's talk about the factors that affect the rate of a reaction. So if you're thinking about the rate of a reaction, that has to do with the number of products produced per second. And it really depends on, it's really directly affected by the number of effective collisions per second. How often are the reactants going to collide in an effective way? And so these factors are all related to how often effective collisions can occur between the particles. So the concentration in molarity for the reactants, or if it's a solid, the surface area of the solid has a big impact on that, right? If it's a solid, if I have a reaction and I've got some chunk of solid, is that going to have a faster rate or slower rate than if I were to break the solid up into tiny particles? Well, a solid can only really react where there is an effective collision. So if it's a chunk and all the solid particles in the middle are not exposed, there cannot be a collision there. A collision can only occur on the surface. So I only have a few effective collisions for the surface molecules at a time. If it's broken down into tiny particles, then the reactant, whatever the other reactant is, it can collide with these things very often. So I'll get much more often, I'll have effective collisions, and I'll start to produce product at a faster rate. So the surface area is important. Molarity is very important. If I have a reaction between A and B, if I only have a little bit of A and there's a ton of B, there's a pretty decent chance that they'll start colliding. But if there's only a little A, I'm only going to be able to make a few products per second because A has to be involved in that collision. If I have a different situation where I've got lots of A's in a small amount of space and lots of B's in a small amount of space, well then they're going to be colliding all the time. So the more often they collide, the more effective collisions and the more product I can produce per second. So this first one is about facilitating collisions. Effective collisions. I mean, they're all about that ultimately. Specifically between the reactants. So I want to add more reactants to a given amount of space. If I add a bunch of solvent and dilute it, so the reactants are mostly separated by solvent molecules, S here for solvent, then A and B are not going to collide very often. And there won't be very many collisions or effective collisions occurring per second, so the rate will go down. What about temperature? If I increase temperature, I'll increase the rate. There aren't really any exceptions to that I'm aware of. And that helps the collisions as well, because if I increase the temperature, these particles will be bouncing around more, they're probably more likely to collide. But more importantly than that, there's also this idea that I have to have the collisions be effective. What does it mean for collisions to be effective? Well, if A and B are moving real slow and they collide, if that collision doesn't have the energy to get to the transition state, if the collision only has maybe this much energy, I can't break the bonds. I can't do the reaction. So effective collisions have to have enough energy to get from the reactant to the transition state. An effective collision has the activation energy present. It's colliding with enough force, enough kinetic energy to provide the activation energy to get all the way up to the transition state. And if it doesn't, it's not effective and it won't produce products. So increasing the temperature, the main thing there is to not necessarily create more collisions, although that helps, is to create stronger collisions. The stronger collisions, a greater percentage of the collisions that occur will have the activation energy necessary to produce the products. And obviously that goes hand in hand with activation energy. So here, if I have a lower activation energy, that's going to be a faster reaction. Right, so this would be like comparing a situation where I've got one reaction pathway that has a high activation energy versus another that has a low activation energy. This is what allows chemistry to work. If every reaction had the same activation energy, as soon as I put reactants together, they would all be undergoing different reactions, right? So if I add a little heat, and my particles start colliding, most of the collisions that occur might have the amount of energy necessary to take this pathway and give me a specific set of products that I'm trying to make. As long as I don't add too much heat, I don't have to worry about the collisions having enough energy to make it up here most of the time. So there may be some collisions, maybe the strongest ones have that amount of energy necessary, but there won't be very many, right? That's why when you're in lab and you're trying to evaporate the solvent, you don't want to heat it up too much. You're just trying to break some of these intermolecular attractions and let the solvent evaporate. If you heat it up too much, you might start providing the energy necessary to undergo other reactions that have higher activation energies. You want to avoid that. So when we're running reactions, the temperature is important because we want to have enough temperature to reach our activation energy for a desired reaction, but we don't want to cause side reactions that would require more energy. Sterics and Orientation. So this will be more relevant once we start getting into some substitution reactions, but just to give you a preview there, there's a specific type of substitution called SN2, and in an SN2 there's an electrophile, which we've been talking about recently. It's an electrophile, it's an electrophilic carbon because there's a leaving group, could be a bromine or a chlorine, could be an oxygen if it were bonded to the right things, and it could stabilize the charges, charge that results there when it pulls the electrons away. And there's a nucleophile. The nucleophile could be an OH or something that has a negative charge and it needs to share its electrons to balance out its charge. So if I want to do a substitution reaction and bring in this OH to replace the Br, I have sterics as a concern. If I put methyl groups here, this reaction is not going to work. The crowding or sterics of these methyl groups prevents the OH from colliding effectively at the site it needs to collide to push out the bromine. So this particular reaction is a great example of how sterics and orientation are both important. In order for this substitution to occur in this manner, in order to push out the bromine, assuming that the nucleophile is going to come in at the same time that the leaving group leaves, it has to come in from the opposite side. There's molecular orbital reasons for that we're going to get into when we talk about this reaction. And there's data that suggests that it has to happen from the back side, which means as the leaving group's leaving, the OH can't come in over here. That's what we mean by orientation. If the only collisions that are effective are the ones where the collision occurs in a very specific spot, or orientation or site, those are probably not going to occur that often. So the rate's going to go down. And so the more specific this is, the more required it is that it be in a very specific location, it's going to slow down the rate. So a lot of organic chemistry reactions are very site specific. They require a collision to occur in a very specific spot on a molecule. So a lot of them are slow reactions. They might be set up to run overnight or over the course of a couple days to give time for all the necessary collisions to occur in the right orientation. And obviously sterics is a problem with this reaction. If I've got these big electron clouds blocking it out, it's really going to be very rare that this molecule can come in here and collide in the right orientation without getting blocked out and bounced off by these other electron clouds repelling the negative. So this reaction would be ultimately too slow to even be practical, because the number of effective collisions occurring per second would be very limited due to the sterics blocking out the specific orientation with which the nucleophile has to attack. And then the last thing that affects the rate is a catalyst. So we're going to get into some specific catalysts later in the semester, but generally what a catalyst will do is to change the pathway. So if I look at the reaction progress versus the free energy, and if I have a reaction that has a really high activation energy, so almost never are the collisions going to have the energy necessary to get to the transition state? Adding a catalyst does not change the reactants or the products. It only changes the pathway. It usually adds more steps, but as long as the steps don't require as much energy, the whole process will occur much more often, because there will be a lot more frequent collisions that have this energy to get to these transition states than there will be to get to this much higher energy that would be necessary to make the product if I didn't have the catalyst present. So that's just basically catalysts in general. We'll talk more specifics about those later. So that should cover some of those bullet points. What else did I put on here? This stuff relates to next week's exams. And so since some of you still haven't taken this week's exam yet, let's just go back to these bullet points. So day 12, the three types of molecular motion are vibrational, rotational, and translational. So bonds stretching and bending is vibration. Bonds and molecules rotating and flipping over in space is rotation. And then if you have a liquid or a gas, the particles flying through space, that's going to be translation or translational energy. Entropy, we talked about that pretty well. How do I assess entropy of the system? I usually look to see if the number of moles is going up or down. How do I assess entropy of the surroundings? I look to see whether the reaction is exothermic or endothermic, and whether the temperature of the surroundings is going to go up or down. How do I determine entropy for the universe? Well, one way to do that is to look at delta G. So if I have some space here, if I have a reaction where I'm able to determine delta S for the system, let's just say it ended up positive, and I can determine delta H for the system, let's just say it ended up positive. Once I know delta H, if it's absorbing energy, I know the surroundings temperature has to be going down. If the temperature is going down, the entropy is going down in the surroundings, because there's particles have less variety in the ways they're moving around if they're at a lower temperature. So if I am looking at the total entropy, I'm adding these two together. It's the system plus the surroundings. If they have opposite signs, I can't really determine the total entropy. If they have the same sign, then I can definitely know whether it's positive or negative based on those specific signs, right? So that's what you look for there. We talked about that. We didn't really talk about this. How will a temperature change affect the spontaneity, or the degree to which a process is product favored? So spontaneity, if something is spontaneous versus non-spontaneous, that's determined by the sign for delta G. So if it's spontaneous, it's negative. If it's non-spontaneous, it's positive. So how do I determine how temperature affects that? Well, the best way to do that is to look at this equation. We have to judge whether the reactants are more stable than the products. Or we could look at whether the temperature increases in the surroundings or decreases. That allows me to determine the sign for delta H. Then we have to look at whether the system increases or decreases in entropy. Right? If there's more moles or more number of particles in the products, then the products have more entropy and delta has to be positive. and vice versa. So the sign for delta G is going to depend on these signs. Ultimately, though, it's the sign for delta S that really makes the difference if we're looking at how temperature affects delta G, because delta S and temperature are multiplied together. So what that means is, if I can determine that the system's entropy is going up, and the temperature in Kelvin will always be positive, and I've got a negative sign here, a negative times a positive is going to give me a negative value. And the more I increase the temperature, the larger that negative number will be when I add it to delta H. So it doesn't really matter what the sign for delta H is. If I increase the temperature enough, and I make a larger and larger and larger negative value to the point where it's larger than whatever the value for delta H is, it's going to make delta G more negative. So an increase in temperature will shift an equilibrium toward the products if delta S is positive. And that is the situation where the products have more entropy than the reactants. So an increase in temperature shifts the reaction toward the side that has more entropy. Let's look at the opposite scenario. Let's say instead of delta S being positive, let's say it's negative. So if delta S for the system is negative, the temperature in Kelvin will always be positive, and then there's a negative sign here. So this term will be a negative times a positive times a negative, and that's going to equal out to a positive number. Negative times a negative is positive, positive times a positive is positive. So in this case, if delta S is negative, then if I increase the temperature, I'm increasing the size of this positive number, and when I add that to delta H, increasing the temperature is only going to make delta G more positive because I'm increasing the size of this positive number. So an increase in temperature will shift. It'll make delta G more positive, which means non-spontaneous, which means reactant favored. So it'll shift the reaction toward the reactants if delta S for the system is negative. Delta S for the system will be negative if the reactants have more entropy. So what this means is an increase in temperature will shift the reaction toward the side with more entropy. And so that's true of both of these statements. And so that's probably the easiest way to remember it. You won't be likely to make any mistakes if you think of it that way and always remember it that way. If I have a reaction and I can look at the states of matter or the number of moles present and I can see one side has more entropy, that's the side the reaction should shift toward if I increase the temperature. See, I'm going to pick and choose a couple of these because we're running a little late on time. We talked about thermodynamics versus kinetics. We talked about reaction rate. We didn't talk about units, but we did say that a reaction rate is the amount of product the amount of products forming per second. It could also be thought of as the amount of reactants reacting per second. So it's usually an amount per unit of time. So it's going to usually be grams per second, but most of the time it will be molarity per second or moles per second, the amount reacting per second. Now we talked about these factors and how they affect reaction rates. let's take a look at this one here. How do I look at the initial rate changes when the reaction concentrations change to determine the order of reaction with respect to each reactant? Let's take a quick look at that. So that's the method of initial rates. The method of initial rates allows me to relate changes in molarity to changes in rate to determine if my reactants are first order or second order or zero order. So we were talking about this reaction earlier, this substitution reaction, and we're going to get into this next week. So I'm going to use this as an example to discuss this concept. So let's say I've got a nucleophile in general, and I've got an electrophile with a partial positive, and it's attached to a leaving group, so the leaving group can leave. And I want to determine if this reaction between them happens in one step or in multiple steps. Right? There's a couple different mechanisms I could imagine. I could imagine the nucleophile comes in at the same time that the leaving group leaves, so the whole thing's happening in one step, all at once. Excuse me. Or I could imagine that the leaving group leaves first. If it leaves first, that would produce a fully positive electrophile, and then maybe the nucleophile comes in and attacks that in a second step. So this would be a two-step process. Either way, the nucleophile is now going to be connected there, and the leaving group is going to be on its own. So I have a nucleophilic attack occurring and a loss of a leaving group occurring. The question is, what order do they occur in? Is it a one-step process? Is it a two-step process? Well, if I look closely at these mechanisms, what I'll see is, in the one-step process, both reactants are involved in the collision. Both reactants have to be around colliding. So if I start with 1 molarity of each of these, and I'm able to measure the initial rate, or once I add those starting molarities together, how often is the product produced? So I'll just make up a number. Let's just say it was 4.0 millimolar per second. I would expect with this mechanism, since both reactants have to be involved in a collision, if I increase the molarity of either of them, it'll increase how often the collisions occur. And that will make the product form more often. Right? If I double the amount of this, I'm doubling how often the collisions will occur. I should be doubling how often the product's produced. So if this mechanism is correct for the reaction, if I were to double this molarity and keep this one the same, I would expect the rate to double. If that were observed, that would tell me that in the rate law, the concentration of the nucleophile is first order. That's what I would expect here. 1 mole of it is involved in this collision, so doubling the amount of it should double how often the collisions occur. Likewise, since this other reactant is also involved in the collision, if I double the amount of that, go back to 1 molar here, go up to 2 molar here, doubling the amount of that reactant, where I'm not changing the other one, should also cause the rate to double. Because if I double the amount of that, I'm also facilitating twice as many collisions per second. I should get twice as many products forming per second. And that would suggest that the electrophile, or so-called substrate with the leaving group, is also first order. And that is the rate law that you can measure experimentally by running these experiments. And when certain nucleophiles and certain electrophiles are reacted, that's the rate law you see experimentally. So that's the method of initial rate. What would the rate law be in this situation if I've got a two-step process? Well, the answer is it depends on which step is the slow step. So let's look at a couple options. Let's say first, maybe this first step is a slow step. What does that mean? Well, if the first step is a slow step, my reaction coordinate diagram would look something like this. The first step would have a higher transition state, the second step would have a lower one, and then I would form the product. It's a two-step process. If the first step is a slow step, like we showed earlier, whenever that happens, the next step would happen pretty quickly in comparison. So it's the first step that's slowing the whole process down. And so in order to get from reactants to products, what really I need to facilitate are collisions that occur in the first step. If I can make those happen more often, then the next step will follow. So how do I make the first step happen more often? I have to increase the amount of particles involved in a collision in that step. The nucleophile in this mechanism is only involved in the second step. So yeah, adding more nucleophile would increase how often the second step happens, but it's not going to speed up the first step, and since that's a slow step with the higher energy transition state, that's the step that's slowing everything down. So in this scenario, if I started with 1 molar of each of the nucleophile and the electrophile, and I measured the reaction rate, and just for a baseline experiment, and then if I doubled the amount of the nucleophile and kept this the same, what would happen to the rate? It would remain at 4.0. Increasing the amount of nucleophile only speeds up the steps that the nucleophile is involved in colliding. If I still have the same molarity of this, it's still breaking apart. The leaving group's leaving at the same rate as many times per second as it would have otherwise, because I haven't changed that. And if it's happening at the same rate, even if I speed up the second step, I'm still only producing product as often as the first step can give me intermediate. And so I don't see an increase in the rate. So that would tell me that the rate is, the rate law includes the nucleophile to this 0th order, or it's a 0 order reactant, because changing its molarity doesn't affect the rate because it's not involved in a collision in the main step that actually affects how often product is produced. If I were to double the molarity of this reactant, then I would see a doubling in the rate, because the electrophile, with the leaving group, is actually first order in this mechanism, right? Doubling the amount of this is going to double how often these things are colliding, and loss of leaving group occurs to produce the intermediate. If I can double how often the intermediate is produced, I'll double how often the overall product is produced. And so that reactant is first order. So that illustrates that idea. We're going to talk again about that in almost the exact same way when we get into chapter 7 and look at the difference between these mechanisms. A few people are still with me. Any other questions at this point? I'll keep going if not.
Could you do one more example of the initial rates, or present it in a way that would be on an exam?
That's a fair question. Yeah, on an exam, I might give you reactants, and I might give you initial rates, and ask you to determine the rate law. So I'd have to give you some experimental data here. So if I gave you this data, how would you determine the rate law?
Could you walk through it? Maybe I'm still a little confused on the method.
Sure. So what I want to do here is to correlate changes in molarity for one reactant at a time, where the other reactant molarities don't change, with changes in the rate. So the rate law always equals the rate constant times the reactants multiplied together, their molarities multiplied together. So we're using the brackets here specifically because the brackets mean molarity. And the exponent is what we're trying to determine. Everything else is the standard formatting for the rate law, the way it's written. So if I double the concentration of a reactant, mathematically, there's only one way I can do that and not see any change in the rate. Because the way this equation works, if I change a number here to keep it equal, this number have to change. Right? If I have A plus B equals C, if I want to keep this equal and I double C, well then I have to double the other side. Otherwise it's not still equal. Right? That's how algebra works. So if I double this reactant and I notice that doing so does not double the rate, mathematically that means the exponent here must be a 0. If it were a 1, if the exponent was a 1, then doubling it would cause the other side to have to be doubled to remain equal. But the rate is not, we're not seeing that experimentally. Experimentally, the rate is not doubling when the molarity of A doubles. So the only way that can be true is if this is a 0, because 2 to the 0 power is equal to 1. So really, if I double something to the 0th power, it's not really doubling it. It's the same as multiplying it by 1, which means the other side doesn't have to be doubled. I don't have to do anything. So the only way the rate can remain constant when I change the molarity of one of my reactants is if that reactant is 0 order. So that tells me the exponent for A. To look at the exponent for B, I want to compare two experiments where B is doubling, but A and C are not changing. That way, if the rate changes, it must be due to the change that I made to B. So I'm isolating the relationship between the molarity change for one of my reactants and the rate change. In this case, I'm doubling the molarity, and I do see that the rate from experiment 1 to experiment 3 doubles. So if one doubles and the other doubles, the exponent is a 1. Right? Doubling C to the first power is the same as doubling to the first power the other substances on the other side. So any two quantities on either side of an equal sign, if I double one, if it's to the first power, then the other side will double as well. So that tells me that B is to the first power. Or other words, I'm taking 2 to the first power. I've got to take 2 to the first power is 2, so I have to multiply both sides by 2 to keep it equal. When I'm looking at C, I can compare experiment 1 with experiment 4. No change in A, no change in B. I'm doubling C. So the relationship between experiment 1 and 4, the degree to which the rate changes is a reflection of that molarity change I made in C, because the other two aren't changing. So if I double C, and I notice the rate goes from 4 to 16, which is a fourfold increase, or a quadrupling, right? I could take 16 divided by 4, and I can see 16 is 4 times larger than 4. So that means that that rate went up 4 times when I just doubled it. Well, that tells me that this reaction rate is really highly dependent upon the amount of C present. And if I double the amount of C, I quadruple how often the effective collisions occur. So mathematically, the only way to get that to work is if this is squared, right? 2 squared is 4. So 2 squared, if I multiply this side by 2 squared, it's the same as multiplying the other side by 4. And that's how I keep it equal. So to square this, I have to recognize that the exponent is a 2. So if C is second order, any factor I change that by is going to end up being squared because of this exponent. And so if I multiply the molarity by some factor and I find the rates multiplied by that factor squared, then I know the exponent is a 2. Any questions about that?
Would that be the final answer then?
Yes, this is the rate law. If the question is asking for the rate law, this is the rate law that you would have. Determine the order with respect to each reactant. So the order with respect to A is 0 order, the order with respect to B is first order, and the order with respect to C is second order. And that goes into the rate law. And that relates to this bullet point right here. If I give you the order, how can you should be able to determine how much the rate will change when the concentration of a reactant changes, right? So that's basically the same thing. So if I tell you that it's second order, and we're looking at a fifth experiment, let's say we're not going to change the molarities of A and B. Let's say I make this molarity 4. If I go from 1 molar to 4 molar, and that's the only change I've made, and I know that if I tell you it's second order, how much would the rate change?
Would it be double?
So if I know it's second order, whatever factor I multiply this by, when I multiply the molarity by some factor to increase it, I'm going to have that factor squared. So because the exponent is squared, if I multiply something and then plug it in here and it ends up being squared, 4 squared is equal to 16. So a 4-fold increase in the molarity would cause a 16-fold increase in the rate to keep these equal. So it would be 16 times 4, which would be 64. The exponent affects the molarity change. Whatever molarity change you have to take that number to the exponent to figure out how much the rate is going to change from what it was at the lower molarity. So if it was 4 at the lower molarity, and I quadruple the molarity of the reactant, quadrupling the molarity to the second power is really multiplying the molarity by 16. And so to keep that equal, the rate has to increase 16-fold, and so I have to multiply 4 by 16 to get 64 for my rate. We can try to look at some other examples of that later this evening at the beginning of lab if you like, Ethan.
Yeah, that'd probably be helpful.
Yeah, I can also look to see if that specific question is going to be on your exam, whether it's worth the time necessarily to focus on that one detail. So we can take a look at that later.
Thank you.
Sure. Why is activation energy necessary? It's necessary to break the bonds that are present initially. So you have to separate attracted particles before you can even start to think about rearranging them into a different form. And energy has to overcome their initial attractions. So the amount of energy necessary depends on how strong the initial attraction is and how unstable it is at the moment that those attractions are broken. So if I have a reaction that has an especially stable bond, it's going to require a higher activation energy to break it. Or if I have a reaction where I've got to break 2, 3, or 4 bonds all at once, well, that's going to take a lot of activation energy to break all those at the same time. So those are the main two factors related to that bullet point. What's the relationship between reaction rate and the activation energy? The higher the activation energy, the slower the rate. Right, that has to do with the reaction coordinate diagram. If I have a reaction that requires me to put a lot of energy in, it's going to be a slow rate. It's only going to happen once in a while versus one where I have a lower activation energy. Most of the collisions will have the energy to do that, and that's going to happen more often. It's going to be producing product in a greater quantity per given time unit. We talked about the next bullet point in our other example. The next two, actually. This bullet point here, there was a quiz question related to that one. So that one was a situation where if you have two possible pathways in competition, how can I use temperature to control which pathway occurs? So, for example, if one pathway has a lower activation energy than the other and this one has a higher activation energy, if I keep the temperature low, that will favor the lower activation energy. And if the temperature is low, most of the collisions aren't going to have the energy to make it up to the higher transition state. So this lower activation energy will be happening often, and the higher one won't happen very often. So I'll get much more product from this pathway. Even if that product isn't as stable as in the end as the final product from the other pathway. So that's the thing. Using temperature, I can control reaction and make sure it doesn't go through a higher activation energy transition state to some degree. If I increase the temperature and get to equilibrium, then I can control which product is produced based on thermodynamics. Because this product has a negative delta G, but the other product has an even more negative delta G, that's the one that's going to be favored when it reaches equilibrium. So time and a high temperature, if this whole thing keeps shifting back and forth, yes, the lower energy pathway is going to happen more often, but if I put enough heat in and time, well, that'll go back sometimes, and then once in a while, if I have a high enough temperature, this will go over the higher energy transition state and it'll produce this product. And since this one's more stable in the end, that one is going to accumulate when it reaches equilibrium. So if I keep the temperature low and don't wait too long, most of my molecules will go through this and I'll get this set of products. But if I heat it up and I can get it to go back, and then forward, and then back, and eventually reach equilibrium, I'll get more of whichever product is thermodynamically favored. So we're talking about kinetically favored at low temperature, and thermodynamically favored at a higher temperature due to the lower free energy associated with that product. So that's what that bullet point there was about. What's happening during the transition state? That's the moment when the bonds are breaking and forming. Breaking and or forming. At that moment in time, that tiny instant that's too fast to even observe, and which makes it completely theoretical, but it matches well with a lot of experimental observations, so it's quite well established. The electrons are in no man's land. They're not in an orbital properly. Normally, electrons exist in an atomic orbital around one nucleus or in a molecular orbital around multiple nuclei. When the bond stretches and is in the process of breaking, the electrons are not effectively in either type of orbital. They're not effectively attracting to really any of the nuclei. And so that makes it very high in potential energy. That's the highest potential energy point in a reaction. Because at that point, where the electrons are not in an effective orbital, there's a lot of potential, because they will immediately move into one orbital or another as the bond finishes breaking or finishes forming. So that's really unstable at that moment for the electrons. So the transition state is always the highest point on these peaks. There's a transition state, there's a transition state, there's a transition state, transition state. Transition state is the highest point in the reaction. Later we're going to talk about transition state pictures. How do I draw a transition state? So for example, if I have a loss of a leaving group, it doesn't matter what this is. So this is like a carbon here. Say there's a leaving group attached. So we use the curved arrows to show where the electrons go, but if you want to draw the transition state, usually you would draw that bond being in the process of breaking and forming. So the bond, if the bond is breaking, it stretches, it gets longer, and the dotted line is meant to show that the electron pair is not yet existing as a lone pair on the product, and it's not really existing as a bonded pair in a molecular orbital on the reactant. It's something in between, and it's really unstable because as the bond is breaking, the atoms are too far apart for their orbitals to overlap and create a molecular orbital, but it's not yet, the electrons have not yet made it to an atomic orbital to exist as a lone pair. So it's kind of in between those two states. It's very unstable. If the electrons are pulled away, they're starting to move toward this atom, so it might start to hold some of their electron density, and they're being pulled away from this atom, so it might start to become positive. But the dotted line is meant to represent how unstable those electrons are during that moment, and that's your transition state. I didn't write any Hammond postulate questions. The relevance of the Hammond postulate won't be clear to you until a little bit later when we see some examples, so I'm not worried about it right now. It's not really that important to know as a concept. It'll make much more sense and be less abstract once we see some specific examples later in the semester and even more next semester. We looked at drawing a reaction coordinate diagram. Just to point out this bullet point here, it relates to this question up here that we talked about. This one here, right? If I give you some information, if I tell you whether it's endergonic or exergonic, how many steps there are, which step is the slow step, then I would expect you to draw a reaction coordinate diagram, making sure the slow step has the higher energy transition state. making sure that the products are lower in free energy than the reactants if it's exergonic, or higher in free energy than the reactants if it's endergonic, labeling the transition states and the intermediates. So that was a good example to illustrate that bullet point. Yeah, and then this last bullet point is right along those lines. Exergonic, endergonic. Exergonic, endergonic, endothermic, exothermic. Those terms relate to a comparison between the free energy or potential energy of the reactants versus the products. It doesn't matter what the transition state is, it's only reactants versus products if you're comparing those two. And that is it for exam 6. Any questions about any of that or anything else?
With the last bullet point, could you repeat what you said with the exergonic versus endergonic, and then the difference between exothermic and endothermic?
Sure. I can definitely do that. So, thermic versus gonic. Or endothermic has to do with plotting the potential energy, which is the same as the enthalpy over the reaction progress. So if I have a starting potential energy and my products end up higher in potential energy, I have a positive delta H. That's endothermic. If the products are lower in potential energy than the reactants, and I have a negative delta H, that's exothermic. Exer or endergonic has to do with plotting free energy versus reaction progress. So in Gen Chem, we mostly just focused on potential energy because we were mostly interested in the heat. Does this reaction release heat into the surroundings because it's exothermic, or does it have to absorb heat from the surroundings to make the products, meaning it's endothermic? We were interested in calculating the amounts of heats involved and all that stuff in Gen Chem. But then we learned about equilibrium and that the sign for delta G is really more powerful if we're trying to understand when it reaches equilibrium whether we get more reactants or products, and that's an important question. It's also important to know whether the reaction releases or absorbs heat. But if you're trying to run a reaction to specifically produce some product, you want to make sure that it's actually going to be product favored and you'll get a significant amount of it. So that's why we're concerned with it being exer or endergonic. And so if I start at some free energy and the products are at a higher free energy, meaning delta G is positive, I know it's endergonic. And I know that this reaction will favor the reactants, will be non-spontaneous under standard conditions. Alternatively, if the reaction produces products that are lower in free energy than the reactants, then I have a negative delta G. And that's exergonic, and that's product favored. So that's what I want if I'm trying to specifically make products. I want to find a reaction that I know will produce mostly products when it gets to equilibrium.
Okay, thank you. That makes more sense.
Sure. Yeah, it's tough. We're trying to fit, like 3 or 4 days of worth of lecture into a review, and there's a lot of stuff, and I would love to cover all of it. There's obviously, even after spending an extra hour beyond the scheduled time, it's tough without having to gloss over things. So, if anyone does actually have more questions, feel free to message me. We can always talk about concepts at the beginning of lab as well. Obviously, it'd be better to do it before that, since you have your exam when we get in there and everything. But you got to keep moving forward. Any other questions about anything? All right, well, thank you to those of you hardcore people who made it through. Feel free to message me anytime. I'll see y'all in lab, and then some of you, obviously, on Tuesday we'll continue with day 15 lecture and keep going from there. So, alrighty. See you later, everybody. Bye.
This was super helpful. Thank you.
Oh, you're welcome.
Yeah, I wanted to say thank you as well, and I'll see you in